So Sn with same expression by change of variables same expression, I am just changing k to j, a change of notation, I will give you a n minus j into. If you call this a n minus j as h j, a is a constant, so I can give any name for it. So a n minus j I am calling as h j. So this expression is same as this expression. Now I must optimize this h of j's such that this is a minimum mean square estimate of the value of sample at value n, a sample number n. Are you with me? It's just a change of. With your discrete system knowledge, what does this mean? What are you doing? You have a shift register or delay line with tau units of delay, unit delays of a length equal to L delays. So if I put Rn here, the value here will be Rn. And what is the value here? Rn minus 1. And what will be value here? Rn minus L plus 1. This you must multiply by weightages. J is equal to 0, Rn must be multiplied by H0, gain of H0, and so on and so forth. And the gain of this will be some number. Because when the L is equal to 1, this is HL minus 1, right? HL minus. And this will be n minus L plus. All this must be added to give you my estimate of S cap n. The equation is just simply this. And these are analog delay lines having a unit delays, and tap it out and multiply with appropriate gains, add them up. The question is, what are these? If you look at this expression, it is very clear this is nothing but a convolution. So, like a linear filter. So, linear system is doing a convolution here. This is the impulse response of the linear system or this. Okay. So, my question is what are these HGs? How do I find? How do I find it? Very clear, because my measure is this. So, you write down what is expected value of Sn minus S cap n whole square, and minimize this by choosing HJs. So, write down what is my this one into this expression. This is equal to expected value of Sn minus S cap n is equal to sigma So what do we do with this to minimize it? Take the partial derivative with respect to every h is j and equate it to 0. So take a partial derivative of this with respect to this. Let's say take partial derivative with respect to hk. Are you with me or not? This square function, so derivative of a square function is equal to 2 times, there is a 2 here, 2 times this multiplied by derivative of the part of it, and in here when you take a derivative with respect to hx, only the term which contains hx in this expansion, which term correspond to Rn minus k. Okay. This should be equal to 0 for every k. So, solution of this set of L equations corresponding to k is varying from 0 to L minus 1. So, there are so many k's, k is equal to 0 to L minus 1. For every value of k, this expected value should be equal to 0. Now, you see what is expectation? Now, one thing observation you must see here is, before I go further, what is the first term here? This is error, right? That is what the definition of the error is. So, this is error and this is a sample of observation sample, and our requirement is estimate of expected value, not estimate, expected value of error multiplied by any sample, any observation sample. This expected value must be equal to 0. What does it mean? This means that the error Monday, this sample should be uncorrelated. So, the optimum filter is that filter which makes such that the error and the observation sample become uncorrelated. Those set of Hs which will make this true is what is the optimum filter. So, this is a very powerful result, what people call it as the orthogonal principle. I do not have to do all this actually. I can simply write this as a requirement because automatically comes out to be that as the requirement, which is the orthogonality principle. That is, every observation must be orthogonal to the error. At that instant of time n. If you now do the expansion there, first term is what? Sn into Rn minus k expectation, and this S and R are random variables which are correlated because R contains S. So, there has to be some correlation between these two, and they are all Whiteson stationary random variables, meaning thereby this expectation is equal to R S K, first term,